Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. Today we are going to cover lecture 23 and this is week 12. Today's topics are triangular wave oscillator, sawtooth wave oscillator and sine wave oscillator. So we have started oscillators in lecture 22, in which we see a square wave oscillator using op-amp, and op-amp was used in both feedbacks, that is in positive feedback and negative feedback. Along with the op-amp we have used capacitor to make the op-amp oscillate, as capacitor is an energy storage element. So for an oscillator at least one energy storage element is required. So next we would now going to look for other types of other shapes of signals that can be produced, that is how can we produce triangular wave or a sawtooth wave and a sine wave. So अभी मैं आपको ये दिखाऊंगा कि किस तरह के सर्किट्स हैं जिससे आप इस तरह की वेव फॉर्म्स प्रोड्यूस कर सकते हैं. तो इसमें हम op-amp को यूज़ कर रहे हैं. op-amp को और कैपेसिटर्स के साथ हम ये ऑसिलेटर्स इम्प्लीमेंट कर सकते हैं. सो हमें op-amps, कैपेसिटर और रजिस्टर्स, इन कंपोनेंट्स के थ्रू हम ये फंक्शनैलिटीज़ और ये वेव फॉर्म्स हम प्रोड्यूस कर सकते हैं. तो अभी हम देखेंगे कि किस तरह से हम जैसे हमने फीडबैक, पॉजिटिव फीडबैक और नेगेटिव फीडबैक यूज़ करके रिलैक्सेशन ऑसिलेटर प्रोड्यूस किया था, जिससे आप स्क्वायर वेव जो है वो अचीव कर सकते हैं. तो अब हम देखते हैं कि ट्रायंगुलर वेव कैसे प्रोड्यूस हो सकती है या साइन वेव कैसे प्रोड्यूस हो सकती है. चैप्टर 14 जो है वो आप इस वक्त जो आप पर्टिकुलरली जो आपके जो साइन वेव ऑसिलेटर्स हैं ये आप चैप्टर 14 में देख सकते हैं. इसमें कवर्ड है डिफरेंट बहुत सारे सर्किट्स हैं जो कि चैप्टर 14 में आपको मिल जाएंगे. आप उनको देख लें. सारे जो ऑसिलेटर्स हैं हम कवर नहीं कर रहे. बेसिक जो आइडिया है वो मैं आपको दे दूंगा. जो ऑसिलेट स्पेशली जो साइन वेव ऑसिलेटर्स हैं उनके जो वर्किंग प्रिंसिपल है और जो सर्किट की जो मिनिमम रिक्वायरमेंट्स हैं साइन वेव प्रोड्यूस करने के लिए वो क्या है और जो कंसेप्ट है उसका वो मैं आपको डिलीवर कर रहा हूँ. सारे जो उसमें जो ऑसिलेटर्स हैं वो पॉसिबल नहीं है अभी कवर करने ड्यू टू शॉर्टेज ऑफ टाइम. सो जितना हम लेक्चर में कवर कर रहे हैं that would only be included in the examination. Okay, so first of all let me see how we can produce a triangular wave oscillator. So this circuit is you have seen in the last class. This is a square wave oscillator in which these resistors are used to provide a positive feedback and a negative feedback is applied through this resistor and a capacitor. So this circuit is a relaxation oscillator and it produces a square wave of certain frequency and time period, and the frequency and time period would be determined by these components. And the relationship of the time period and frequency we have developed in the last class. You can see those derivations in lecture number 22. So if I have a square wave, then we know that we can, if we apply a square wave to an integrator, then the output of the integrator would be a triangular wave. So this circuit, you can see that this is a simple integrator. This is an ideal integrator with a capacitor in the feedback, in the negative feedback, and input is applied at the non-inverting side through this resistance. So this circuit is a simple op-amp integrator, and we know that for an op-amp integrator, if we apply a square wave to an integrator, it will give me the RAM output. So as it is inverting integrator, then when input is low, output would ramp up, and when input is high, the output would ramp down. So you can produce a triangular wave from a square wave. So this is the circuit of an triangular wave oscillator. Next is sawtooth wave oscillator. In this oscillator, this is the circuit which produces a sawtooth waveform at the output here. Again, we are using an integrator. You can see that this is an integrator in which input is a square wave and output is a triangular wave. Output should be a triangular wave, but because of the this setup that is applied on the non-inverting terminal of the op-amp, this circuit has the capability of producing a sawtooth waveform in which the rising slope and the falling slope can be made different. In this circuit, you can see that our triangular wave has both rising and falling slopes are slopes equal, and this would be a pure triangular waveform. But if the rising and falling slopes are unequal or different, one is high, one is lower, and the other one is higher, or vice versa, then the resulting waveform is a sawtooth waveform. So by setting the potentiometer arm or moving the potentiometer arm from left to right, you can modify the slope, rising and falling slopes of the output waveform. When the potentiometer middle arm is exactly at the center, then you can see that at this middle of the potentiometer, the voltage would be 0, because this is a positive potential, this is negative potential, and at exactly at the middle point, the potential would be 0, and this corresponds to the ground potential here at the non-inverting terminal, which means that the output would be a perfect triangular waveform. Otherwise, if potentiometer is shifted from the middle either towards the left or towards the right, the waveform would change to waveform would change from triangular to a sawtooth waveform. Either rising slope would be higher and falling slope would be lower, or vice versa. The output of the integrator is fed back to the input of a Schmidt trigger, which has a positive feedback, and because of the fact that with positive feedback this circuit has hysteresis and creates an upper trigger point and lower trigger points. Next topic is sine wave oscillator, in which we will see how op-amp can be used to produce sine wave. So we start with a conceptual circuit and see what are the necessary and sufficient conditions to build this circuit and produce sine wave. So first of all, look at the circuit and try to recognize this circuit in which op-amp is used in negative feedback and input is applied at the non-inverting terminal. So this circuit is basically a non-inverting amplifier whose gain is determined by these two resistors, and this is the formula 1 plus R2 by R1. So the output of the circuit would be a gain times the input. So this is the gain and this is input. Now if I set V in as 1 volt sine wave, and the values of these two resistors are R1 is 1 kilo ohm and R2 is 2 kilo ohm, then with R2 2 kilo ohm and R1 1 kilo ohm, the gain would be equal to 3, and if input is 1 volt, then output would be equal to simply 3 volts. So if I apply a sine wave of 1 volt peak, then I will get a sine wave of 3 volts peak. So this signal is 3 times amplified by this circuit. Now take this output, which is now sinusoidal because input was sinusoidal, and feed this signal back to the input through a feedback block represented by beta. Now if this block takes an input at this point and produces an output, and the gain of this block is 1 by 3, that is, this block divides any signal that is applied at this point and produces a signal which is 1 by 3 times this signal. Then if 3 volts are applied here, we will get 1 volt at this point. So what this block is implemented with, we will see later on, but this is a feedback block whose gain is 1 by 3, and if a 3 volt signal is coming into this block, this block will reduce this signal to 1 volt. So this is an attenuator block whose gain is 1 by 3, and that is the signal is divided, the value of the signal is divided by 3. So with 1 volt here produced here, and this signal is now fed to the non-inverting terminal, and at the moment this signal is fed to the non-inverting terminal, the original signal is removed that we applied here, a sine wave of 1 volt here. At the instant this feedback signal is connected at this point, this would be removed, and this signal would now being serve as the input to the to this circuit or this amplifier, which is a non-inverting amplifier, and this non-inverting amplifier would amplify this signal coming at this point by its gain, which is 3. So with 1 volt coming here, this signal will be amplified to 3 volts. These 3 volts are fed to this block, which divides this signal and make it again 1 volt. This 1 volt is again applied as input, and the circuit again amplified 3 times and produces 3 volts. So this cycle or this chain of action would be repeated continuously, and a sustained sine wave oscillation will be maintained at the output of the oscillator. So this is the concept, but we know that for any oscillator there is no input. the circuit should produce an oscillation by itself, so there must not be any input applied. Just for establishing the concept how this sine wave oscillator can produce oscillations, we are applying an input, and then once the output is produced, this output is regenerated and applied at the input, and input is removed from the circuit. In actual circuit we will see how the circuit would produce the oscillations by itself and would not require any input to start the oscillations. So here you can see that we have two important conditions that are required to be met in order to produce any oscillation from a circuit, especially sinusoidal oscillation. So one is the loop gain, that loop gain should be equal to 1, and the second is the phase angle between the output and the input, that should be equal to 0. So the phase between these two signals, that should be equal to 0, that is these two should be in phase, or the phase difference between the output and the feedback signal which serve as the input, that should be equal to 0, that is these two signals should be in phase, and the loop gain should be equal to 1, that is the overall gain, that is forward gain and the feedback gain. The product of these two should be equal to 1, that is, as you can see, the forward gain is 3 and feedback gain is 1 by 3, so 3 into 1 by 3 would be equal to 1. So forward gain is provided with these two resistors and feedback gain is provided with beta, so 1 plus R2 by R1 into beta should be equal to 1. So next we see how this concept is implemented in Wien bridge oscillator. So next topic is Wien bridge oscillator in which circuit will produce sinusoidal oscillations when this circuit is power upped. So you can see that this circuit is the extension of the conceptual circuit that we have seen in previous slide, that now a feedback block is now replaced with these components, and the forward gain is set by these two resistors R1 and R2. So this circuit will oscillate only at a certain frequency at which these two conditions are satisfied, that we have seen that for any oscillator, any sinusoidal oscillator, these are the necessary conditions which must be satisfied to generate any oscillation. So this circuit will oscillate only when the phase difference between the output and the feedback signal is 0, and that is the phase produced by this feedback block is 0, and the loop gain is 1, that is the feedback gain and the forward gain. The product of these two is equal to 1. Now for the loop gain to be equal to 1, the forward gain is 1 plus R2 by R1 and feedback gain is beta, it would be equal to 1, where beta is equal to, beta is the transfer function which is Vf by V naught. So at oscillation frequency, the value of beta should be equal to 1 over R2 by R1, which is equal to 1 by 3. and the angle between feedback signal and the output signal should be equal to 0 at that frequency. Let we derive the transfer function of feedback ratio Vf by V naught. So this circuit is the feedback block is redrawn here with the output shown on the left and the feedback on the right, so that we can compute the ratio of Vf to V naught here like this, and we are representing the capacitive reactance in the Laplace domain as 1 over Cs and resistance as it is. So these two components are in series, these two are in parallel. They can be combined, these two bits can be combined to form impedance Z1, and these two can be combined to impedance Z2, and where Z1 is equal to R plus 1 over Cs, and Z2 is the parallel combination of these two, R in parallel with 1 over Cs, and by manipulating this expression, Z2 will become equal to R over RCS plus 1. Then by using voltage divider formula, Vf by V naught would be equal to Z2 over Z1 plus Z2, and then from this we can write it as taking Z2 into the denominator as 1 over 1 plus Z1 over Z2, and 1 over Z2 is Y2, which is admittance. By plugging the values of Z1 and Z2 in this equation, we end up with this result, and then after manipulating we arrive at this expression. Then replacing S with j omega, this becomes j omega RC plus 1 over j omega RC. We can shift the j up by this becomes negative, and now we can take j common, so this would be the expression now, and from this expression we can see that this transfer function is a complex function. It has real and imaginary terms, so this transfer function has both magnitude and phase. We know that for these two signals to be in phase, there should not be any complex quantity, that is the j term should be equal to 0. So for that, at a certain frequency where omega is equal to omega naught, and this at this frequency, this imaginary term, if this imaginary term is equal to 0, then from which we can find out the value of omega naught as 1 over RC, and omega naught is 2 pi f naught, and f naught would be equal to 1 over 2 pi RC, and at this frequency, at this particular frequency, the imaginary term would be 0, and the output and the feedback signal would be in phase and having the magnitude equal to 1 by 3, because if this term is 0, the ratio would become equal to 1 by 3. So if these two conditions are satisfied, that is phase difference is 0 and the magnitude is magnitude of the feedback transfer function is 1 by 3, and if we already set the forward gain as 3, the forward gain of this circuit is set by these two resistors, and if R2 is set as 2 kilo ohm and R1 is as 1 kilo ohm, then the forward gain would be equal to 3, and feedback gain is now established as 1 by 3. then this circuit will start oscillations. This makes the circuit to oscillate at this frequency and produce a sine wave at the output. So this is about the sine wave oscillations, that is how sine wave oscillations can be produced by meeting and satisfying these two conditions. So at this point it is important to understand the basic principle of sinusoidal oscillators, and there are different oscillators, oscillator circuits which are presented in this chapter, which are based on these two principles and produce sine wave oscillations. As far as exam is concerned, the topic which we would cover in the lectures would be included in the examination. I will try to give you assignment from this chapter as well, so that you become comfortable in these topics. So that's it for today. Thank you. Allah Hafiz.